My name is Muhammad Imam Azizan. So I will explain about the calculation result. So here is the calculation before we do the simulation. So the summation given is here. As you can see, G1S equal to K over in bracket S plus 12 and in bracket S square plus 4S plus 8. And we just simply expand the bracket below, and just for the K is already given K is equal to 200, and just substitute the K. And that's we got for our transfer function. And for the third order system, which we want to use for the simulation, is 200 over, we just took the first transfer function here at above and just divide by 1 plus the transfer function above again. And then we got the third order system here, the value that I already calculated. So next, here we start with the open loop transfer function, which is the third order system that we got here, and we already given the characteristic equation, and we match this with the standard form, which I already mentioned at the characteristic equation. So from coefficient comparison, we derive three equation and solve the cubic. Here the three equation, as you can see, and we got p cube minus 19p p square plus 85p minus 410 equal to 0. This gives us the pole, a real pole at p equal to 15.18 and complex conjugate poles at 1.91 plus minus 4.83 J. So next we verify the dominance using the ratio as the formula given. So for dominance, which is 7.95 as you can see for the result, which is greater than 5, confirming that the compact poles are dominant. We then calculate the system response characteristic, which is, as you can see the equation at the left, which is the natural frequency Wn equal to 5.2 radian per second, and the damping ratio. We also get and the value for damping ratio is 0.368. And after that, we calculate the settling time, which is 4 divided by the calculation given there, which is we got 2.09 second. And for the peak time, we just simply substitute all into the equation, and we got 0.65 second. So for the percentage overshoot, it is approximately to 28.8% based on the calculation I already did. So that's all for me.
My name is Muhammad Amiradi bin Sharuddin. Now I would like to show you about the simulation. First, as you can see, the graph characteristic is underdamped because it has overshoot at the 0.7 second. From this graph, it will get the peak time, settling time, and overshoot. And the value of peak time is 0.7 second, and the value of settling time is between plus minus 2%, so the value is 2.12 second. Next, the value of overshoot is 27.56% from the steady state. Now we go to the comparison between calculation and simulation. Start from peak time is 0.7 second, while the calculate peak time is 0.65 second, and the percentage error of peak time is 7.7%. Next, simulation settling time value is 2.12 second, and the calculate settling time is 2.09 second, and the percentage error is 1.5%. And for the percentage overshoot, the simulation value is 23.5% lower than theoretical value is 24.4%. The percentage error is only 4.3% difference. And last, the simulation result close correspondent with the theoretical prediction and confirmation the model is correct. The observation minor difference are characteristic due to the ideal assumption in theoretical deviation, and numerical approximation fundamental to simulation, and rounding error or simplification in the parameter value. Now let's see the state space. It have a 5 step, and first is writing the transfer function in linear form. Cross multiple the value ys and cs. Second is a convert S domain to the time domain using taking inverse Laplace transform while get the operator. And third is phase variable to make a phase vector. Let's x equal to y, and x2 is first derivative and x3 is second derivative. And next step is develop dynamic vector for x3 is from the differential equation and need to rearrange. And last step is express metric form x equal to ax plus bu and y equal to cx plus d, and y is equal to x1, and you get the value of y is 100.
Assalamualaikum dan salam sejahtera. My name is Nurkhalina Syafiqah binti Muhammad Fauzi. Now I will explain about the stability of the system. So as you can see, this is open loop transfer function of the system. So to analyze the stability, we consider the characteristic equation of the closed loop system. So we use the formula 1 plus G1S Hs equal to 0. So we have to substitute the G1S into the formula. So we will get 1 plus 200 over S power of 3 plus 19S power of 2 plus 85S plus 210 equal to 0. So we have to derive the equation to get more suitable equation. So we get S power of 3 plus 19S power of 2 plus 85S plus 410 equal to 0. That will be the characteristic equation. Next, Routh-Hurwitz table. To check the stability, the Routh-Hurwitz table is created from the characteristic equation. So, the entries in the Routh table are calculated using the Routh-Hurwitz formula. So, to compute 63.42 as one row, we use cross multiply S3 and S2 and divide by first column of S2. So 19 multiplied by 85 minus 1 multiplied by 410 divided by 19. So we get 63.42. We use the same formula in the S0 row. According to the Routh-Hurwitz criterion, the system is stable if all elements in the first column of the Routh table are positive. So as you can see, the first column from the S3 to S0, all of them are positive. So it means the system is stable.
Hi, my name is Marcelina Wilfred, and now I am going to explain the calculation for the step input Kp. The formula is limit s approaching 0 gs. We change the value k to 200 constant, so we will get the final answer 0.9524. To find the steady state error, it is equal to 1 over 1 plus Kp. So we just put in the value of Kp and we will get the final answer is equal to 0.5122. The next one is finding the RAM input. To find the RAM input Kv, the limit s approaching 0 s times Js. So we put in the value and then we will get this, the final answer is 0. The steady state error is equal to 1 over Kv. Put in the value of Kv equals 0, so we will get infinity. Next one is parabolic input. The equation is limit s approaching 0 s squared Gs. Put in the value and then we will get the final answer 0 as well. For the steady state error, we will get infinity too, since the steady state error for parabolic input is equal to 1 over Ka. The conclusion, this system is underdamped as shown by its 27.56% overshoot and oscillarity step response. The measured and calculated values: peak time 1.7 seconds, settling time 2.1 seconds, align closely, confirming model accuracy. Routh-Hurwitz analysis shows all poles lie in the left half plane, so the system is stable. As a type 0 system, it achieves a finite steady state error for step inputs, but infinite error for ramp or parabolic inputs.